Sup everyone, I'm back. Alright, so I am going to do the trapeze, the circus performer one here, so that's number 30 in chapter 6. It was requested by a lot of period 2. So it basically says, after a mishap, yeah, that doesn't look good. So after a mishap, a 76 kilogram circus performer clings to a trapeze, which is being pulled to the side by another circus artist, who is shown here. There. Calculate the tension in the two ropes if the person is momentarily motionless. Include a free body diagram in your solution. Because, of course, whenever you're in any sort of danger, it's best to, turn it into a physics problem and calculate the tension forces. Because why not? All right. So I started by drawing a free body diagram, and I'm going to get to that in a bit. I do want to show, I just posted this link to your guys' Schoology. It was something I did not make, but stole from somebody. So, haha. It's called Traffic Light Equilibrium Simulation. So this is similar to what we did with the Spider-Man thing. With the Spider-Man thing, though, the thing was... the Spider-Man thing is similar to this traffic light problem right now. So we see a free body diagram of the traffic light, and we got, but each of the angles are equal here. And so the tension forces are going to be equal as well. You can see the tension forces up here. But what's kind of cool about this simulation is I can change where the traffic light is and the angles. And by doing that, it changes the free body diagram and the forces. I can even change the weight, make it bigger. You can see those tension forces get bigger because this is an equilibrium problem. Equilibrium meaning that the acceleration in the x and y direction is going to be 0. And that basically makes it so all these forces have to add up to 0. And so you can see all the different combinations that you can make. So yeah, that's pretty cool. Going over here. Whoop. Okay. So, all right, one of the first things I did was I drew a free body diagram here. Oh, let's also take into account her mass is 76 kilograms. And so I'm going to look at my free body diagram here. This could probably be a little bit bigger, just so we got more to work with here. And so I basically used the diagram that they gave me here and converted it into my free body diagram. I'm going to use T1 instead of our usual FT because just for simplicity's sake. So there's definitely mg going down. That's her weight right there, or the force of gravity. And then we got T1 pointing at an angle in this direction. And then we got T2 pointing at an angle in that direction. The kind of trippy thing here, though, is that they give you the angle here as being 10 degrees with respect to the horizontal, while the angle they give you here is 15 degrees with respect to the vertical. So that's going to kind of change our trigonometric functions right there. You could just as well, this is 90, right? So you can make this 75 degrees, and then you could use your sine and cosine as you usually do. In fact, that's what I did in my solutions. But this time around, I'm actually going to do it using the other way just to show you both ways work. So again, I wrote out, though, so before I had this, all these components were missing. Whoops. I'll just draw it. So my free body diagram was like this. And then, but I can see I got two misbehaving vectors here, and so I would need to include the x and y components of T1 and the x and y components of T2. So, and then by doing that, I need to find out what T1y, T1x, T2x, and T2y are in terms of T1 or T2. And so you can do that basically using trigonometry. For T1, this is 15 degrees. That means T1x is going to be opposite. So that's sine. So T1x is T1 sine of 15. And then for T1y, well, T1y is adjacent to the 15 degree angle. So it's going to be T1 cosine 15. Next up, we got T2. T2y is opposite of the 10 degrees. So that's going to be T2 sine of 10. And then T2x is adjacent to the 10 degrees, so it's going to be T2 cosine 10. So there's those. Okay, so next up now, I'm going to apply the second law in an equilibrium condition. So I'll start with F net equals MA. But again, this is equilibrium, so when I plug this into my X component and Y components stuff, well, this is going to be, so again, if the vector points in the same direction and is the same magnitude, it's the same vector, even though this is actually just a component, but I can, it's easier to do the second law when you move these over toward the dot, so that's what I'm going to do. Uh-oh. And T1Y. And there we go. So we got, so in the X direction, you can see that it's really just the battle of these tension forces along X. So it's going to be T1X minus, oops, sorry, T2X, that's the one going in the positive direction there, minus T1X, and that's going to equal, so in equilibrium, the acceleration is 0, 0 times the mass is going to be 0. All right, let's do the same thing in the Y direction. So in this case, I got T1Y and T2Y pointing up, and then mg pointing down. And again, it's equilibrium, so the acceleration is 0. And there we go. All right. So that basically means that I've got, well, let's plug in, because I know what T2x is and T1x is. So T2x is going to be T2 cosine 10. And if I add T1x to both sides, that means it's going to be equal to T1 sine, right? Yeah, sine of 15. And that's kind of my first little relationship right there. All right. So for the y parts, I'm going to add mg to both sides, and then also in the same step, so I'm going to add mg to both sides. And then in the same step, I'm going to plug in T1y and T2y. So that's going to give me, let's see, T1y is cosine of 15. So T1 cosine of 15 plus T2y is T2 sine of 10. Yes, that's right. And then equals mg. And there is my second relationship. So, okay, I know everything. I know the mass they gave me for the trapeze artist is 76 kilograms, and I know baby G I'm going to approximate to 10. That means all I really have is two unknowns, T1 and T2, and same over here, T1 and or T2 and T1. So I got two unknowns, two equations. I'm going to need to use some sort of elimination or substitution method to solve. I'll let you guys know the easiest way to do this is substitution method. So I'm going to take this equation here, and I'm going to isolate, let's say T1. I'll isolate T1. So this is T2 cosine 10 equals T1 sine of 15. So I'm going to isolate T1, divide both sides by sine of 15. Cancel, cancel. And I get T2 cosine of 10 divided by sine of 15 is equal to T1. And now what I'm going to do is take all this nonsense and plug that in for T1. So that's going to lead me down here. Let's change the color a little bit. So that's going to be T2 cosine 10. You see that mistake I just made? That's where a lot of the mistakes show up in this, is the math gets a little much. Times cosine of 15 plus T2 sine 10 equals mg. And you can see I got T2 terms in both of these, so I can factor the T2 out. That's going to give me T2 times cosine 10 times cosine of 15 divided by sine of 15 If you wanted to get fancy with your tangents and all that, you can definitely do that, but I'm not gonna. Sine of 10 plus sine of 10 equals mg. Last thing I need to do is just isolate T2, so I got to divide by all of this garbage. Okay, so that's going to give me T2 equals, let's write the mg part, so it's going to be mg over, it's going to equal T2. So cosine of 10, cosine of 15 divided by sine of 15 plus sine of 10. Yeah, and so I can plug in. Well, let's just plug in the mass. The mass is what is the mass? 76 kilograms times 10. That's baby G. So this is going to be, let's see. So I'm plugging all this into my calculator. I should maybe use like one of the, never mind. Cosine 10 times cosine of 15. I'm starting down here. I usually do the more complex thing and then divide all that by my answer and things like that. So times cosine of 15 divided by sine of 15 plus sine of 10. Make sure you're in degree mode. And then I have 760 essentially divided by my answer, and I get 197 for T2. Newtons. Got it. All right, and then in order to get T1, well, I know T2. I can go back to any one of these equations. I'm going to think that this is the simpler equation, and I'm going to do that, and, oh, wait. Oh, yeah. I can actually go back to this one that I already isolated, T1, and that's going to give me my answer for T1. But really, you can plug it into any one of these. So let's see, let's use yellow. So this is going to be T2 cosine of 10 divided by sine of 15 equals T1. And I know T2 now, it's 197. So it's going to be 197 times cosine of 10 divided by sine of 15 equals T1. So that means T1 is going to equal, drum roll, cosine of 10 divided by sine of 15 times 197, 750. Hopefully that's all right. Okay, so yeah, 750 newtons for T1, 197 newtons for T2. So again, the big idea here is you're drawing a free body diagram. You want to split up any misbehaving vectors. That's what we did over here. And then you apply the second law. But this is a special case scenario where it's equilibrium. So the acceleration is going to be 0. And basically, it's again just kind of dealing with the algebra here, which is the challenging part. But yeah, if you're consistent, you'll get T2 197, T1 750. So hopefully that helped. All right. See you guys. Bye.